Hello students, so today we'll discuss about a few topics related to nuclear and molecular spectroscopy. We'll start first with Jj coupling. Now Jj coupling is a spin orbit term, and we'll see later on that it is a Hamiltonian. When the Hamiltonian predominates the residual electrostatic interaction and spin-spin correlation, then Jj coupling comes into existence, and it is the result of strong spin-orbit interactions between the angular and the spin moments, and the interaction actually takes place for an individual electron. They are strongly coupled to form A. For each individual electron, L and S will couple to form a J. Total angular momentum, which can be expressed as J into J plus 1. So the value of J lies from L minus 1 by 2 to L plus 1 by 2. This S, L is this 1 by 2 is basically this S, spin angular momentum. Now, as a result of this residual electrostatic interaction and spin-spin correlation, each electron is less strongly coupled with one another to form total angular momentum J, as we have already told. Now let's take an example to get here. For example, if it is a 4p and 4d state, so for the p electrons we'll have L is equal to 1, and for the first electron say 1 by 2, and so the J will be 1 plus 1 plus 1 by 2 and 1 minus 1 by 2, so that makes two values of J, 3 by 2 and 1 by 2. Similarly for the d electron, when L2 is equal to 2 and S2 remains 1 by 2, so it will be 5 by 2 and 3 by 2. So we get two sets of values. One is 1 by 2 and 3 by 2. Another is 3 by 2 and 5 by 2. 1 by 2 corresponding to these two, 1 by 2, 1 by 2, 1 by 2, 5 by 2, and 3 by 2 again corresponding to these two, 3 by 2, 5 by 2, 3 by 2, 5 by 2. Now these two will again virtually add, so they can act, so we are getting 1 plus 1 by 2 and 3 by 2. So virtual addition actually takes place in this form. So we have say 3 by 2 and 1 by 2 like this. So they can act 3 by 2 plus 1 by 2 to make it 2, or they can act 3 by 2 minus 1 by 2 to make it 1. The 3 by 2, so this spin can add up with this spin to make the total spin 2, or it so happen that this is say 3 by 2, then the 1 by 2 may act in the opposite form. This is 1 by 2, so the total spin that is left is only this amount, so that is again 1. So that's how 1 and 1 by 2. And so similarly we can also have for 1 by 2 and 5 by 2. So 1 by 2 plus 5 by 2 will give you 3, and 5 by 2 minus 1 by 2 will give you 2. So this is the case of other sets. So we are getting 3. So it is 3 plus 3 by 2 is 3, and 3 minus 3 by 2 is 0. So all the values in between, this is actually called virtual addition. So these four set of values we obtain, and the selection rules, there is J is equal to 0, delta is equal to 0, and plus minus 1. Now let's come to the Hamiltonian, as I told you. So when there is a spin-orbit interaction, the Hamiltonian is given as H is equal to alpha L dot S, and this is the total angular momentum, J is equal to A plus S. So we take the square, and so this interaction term can be obtained as 1 by 2 J square minus L square minus the square. Okay, now let's go on to another topic. This is all about molecular spectroscopy. Now, if you come to the nuclear spectroscopy, there is an interesting aspect called magnetic resonance, and it is very popular in. This is the basic principle behind the nuclear magnetic resonance spectroscopy. So, if mu is the nuclear magnetic moment, and angular momentum is given as h cross I, so mu can be written as equal to gamma h cross I. Since now the reason it is written that, and since mu and this I is the angular momentum of the nucleus, so magnetic moment and angular moment of the nucleus are parallel, so they can be written in the similar form. And this gamma is the ratio between these two. This is called Galvanic Ratio, as similar as it gets in the case of molecular atomic spectroscopy. At this point of time, if we apply a magnetic field, the magnetic field has been applied here. So this magnetic field interact with the nuclear magnetic moment, and we get the following way. Use a dot Bz to apply. We assume that it is applied in the z-axis, so there will be a dot product of these two. And since mu is equal to gamma h cross I, so we come up with this expression, gamma h cross I z into B0. Again, this Iz can be expressed in terms of the azimuthal quantum number. So I stands from plus I to minus I. So putting that value of Iz, we get the total interaction energy term minus Mi gamma h cross into Bo. Now, this due to when the I has I is equal to say 1 by 2 due to the spin of the electron. So it leads to two values of Mi. So indicates that when applied magnetic field given, so a nuclear state will split up into two states corresponding to two values of Mi, 1 by 2 and minus 1 by 2, and the distance and the difference, energy difference of the two will be expressed as h cross omega 0, and it will be equal to 2 into mu into u0. Now this omega 0 is actually nothing but the precisional frequency. So if a magnetic field has been applied in this direction, the z direction, say, let's take it as z, and this is the nucleus. So it will precess around the magnetic field, and this is called Raman position, whose frequency is expressed as omega 0. And if you cut it, so this comes up to be, this is the original frequency, gamma B0 by 2 pi. Another thing is that when we are applying a magnetic field, initially there will be some electron in the spin-up state. Some electron in the spin-up state, we take the state as alpha, and some electron in the spin-down state, we take that as beta. And the difference, and any population, as we know, is expressed as J by 0 by Boltzmann distribution. So this energy difference between the upstate and downstate. Now this concept has been utilized in nuclear magnetic resonance spectroscopy. What is done in nuclear magnetic resonance spectroscopy is that a magnetic field B1, which is a radio frequency pulse, is applied, and there is a perturbation of the spin population. That means the alpha state with spin up and beta state with spin down. There is a change in these spin populations, and this occurs when there is a resonance taking place. So if this is the case, that the magnetic field has been applied, and this is the spin upstate and spin down state. There is the radio frequency pulse, so it generates an electric field P1, and with net magnetization M0, and we will have a corresponding Raman position omega 1. So when there is a matching between omega 1 and omega 0, then there is a resonance taking place. And due to the resonance, something called spin flip takes place. So spin flip means that if some states are in the number of states in the having spin up and spin down becomes equal. Because if there is a shortage of states in the spin down, that will be compensated by spin flip. Spin flip will take place to convert a spin up state to a spin down or vice versa. And that takes place when this frequency of precision is gamma 1. So after the spin down and spin up state has been taking place, so the number of population in both the states are equal, and there is no both the states are equal, so there is no net m along the z-axis. No m becomes z-axis. So net magnetization is the m0 initial magnetization. At this case, when this B1 is turned off, again, so the magnetization turns to mxy, the difference between these two, and this mxy will again try to will continue to persist along B0 with omega 0, the magnetic field of the nucleus. And the received signal, we take it as the NMR signal. Now, in the NMR signal, there is a relaxation time given as T2. It's nothing but the full width of maxima of the frequency versus intensity. And this is the time taken when the spin flip is taking place. So the exchange of energy between the excited and the lower energy nucleus, that means that basically the time to take to flip the electron, so that an exchange of energy can take place. This is given as the transverse relaxation time. So when there is no magnetic field, when the RF pulse has been turned off, the magnetization in the XY direction is represented as minus T by T2, and this is the expression of the population ratio between the spin up and the spin down state. So this alpha is basically the spin up state, and beta is the spin down state. And as you know, the energy between these two is this expression. Now from here we can see that if there is an increase in this energy gap between these two, this will cause an increase in the ratio of the number of electrons in the spin up state and spin down state, and it will also increase the value of gamma. So basically it will increase the sensitivity, or the NMR signal will be more enhanced. Okay, so this is all about nuclear magnetic resonance spectroscopy.